Hello, everyone. Welcome to the Passive Seismic webinar series. Today, we have Andres Chavarria presenting distributed acoustic sensing applications in engineering and geoscience. Andres Chavarria is OptaSense's Oilfield Services Technical Director. His current focus is in the use of distributed sensing fiber optic data for engineering and geoscience applications. He has a background in borehole seismology, MS and BSP, and was previously the geophysical processing manager at OptaSense SR 2020 and Paulson. He has conducted work in other areas of geophysics, including geothermal, mining, and groundwater. And he holds an engineering degree in geophysics from the National University of Mexico and a PhD degree in geophysics from Duke University. And don't forget, this is a series. In January, we will have distributed fiber optic sensing development, urban infrastructure management applications with Michael Montgomery on January 6th. So be on the lookout for that presentation as well. And with that, I'm going to leave you today with Andres. Andres, the audience is yours.
Thanks for the introduction, Annabella. Let me start sharing my screen here. Perfect. Okay, thank you everyone for attending. This is one of those presentations where when I want to cover a lot of ground, I know certainly our industry, certainly our geophysics industry has changed quite a bit over the last couple of years with this whole energy transition, and we do find a situation where essentially many things are moving. So I think what I wanted to do here was showcase how this technology of DAS, of distributed acoustic sensing, has really opened the door to many of the skill sets that we all have, that we've been using for many years, perhaps in more oil and gas type of setting, but how all of those skill sets and how these new tools are enabling us to go really beyond traditional geophysics and really using all of those toolkits to look at, let's say, pipelines, border, transportation, utilities. So I'll talk a little bit about how all of these systems really have really changed the way we do geoscience and engineering, because they're very, very versatile in nature. So I'll start by talking a little bit about how distributed fiber sensing works. So traditionally, we have an interrogator unit that sends a light pulse down a fiber, and then a portion of that light is going to be backscattered. So traditionally, we will be displaying this data in real time. So again, this is a real-time surveillance where essentially, as you inject the light pulses into the fibers, and this can be fibers in a borehole or on the surface, whenever there's a disturbance, we're going to be basically tracking with respect to depth and time where those disturbances are located. Initially, when we first developed this technology, we were focusing on seismic signals. And nowadays, we know that we actually can measure significantly more things beyond seismic. So this waterfall display, again, we can basically use it to display, let's say, things like microseismic data. And I will get a little bit more in detail into this in a little bit. But part of the advantage of this technology, again, is that we are really surrounded by fiber. Certainly, fiber for telecommunications, for other uses, and increasingly, certainly still in the energy industry, we still have a lot of assets that are being instrumented with fiber as part of the permanent surveillance. So the first DAS ever that we acquired was back in 2007. So this was literally just connecting an interrogator unit with this box connected downhole, and again we acquired a fiber size data. We saw some hints of signals, so that was encouraging enough to develop the technology, and I can say develop the DAS industry in general. So now a few years later, now we are at a significantly higher signal to noise. We are getting a very good data quality seismic, and we are doing all types of seismic surveillance. So again, certainly from a reservoir development, there's many uses for these types of use. We can change now. You have different sensitivity, different spatial resolutions that you can achieve with these types of systems. And perhaps the newest development sits on the long range. So again, increasingly, since we're connecting to fibers that are very long in distance, it has that length has basically forced us to come up with technology that allows us to basically still get backscattered light from very far distances from where our interrogator unit is. So I won't talk a lot as much about the interrogators and the nuances on how they work. I really want to focus this more on the application side of things, because I think this is really I want to showcase basically the things that we can do with this data. But of course, I'll start with the reservoir development, with the traditional geophysics and seismic application. And here I'll just do one example on depth migration for this presentation. So I don't want to focus too much on this, but this is again, of course, something that is very common right now, very popular, a very hot topic in geosciences, which is carbon storage. So again, all of this seismic data that we have been collecting from different boreholes, we know that we can use all of those active seismic sources to do a baseline seismic images of the reservoir. We can get our monitor seismic images of the reservoir. And more importantly, we can see the time-lapse changes. So again, all of this data is processed just like a standard seismic data. It just happens to be recorded with a fiber optic. So in this case, of course, for CO2 mapping, an important aspect of this is basically mapping what the extent of those plumes is with respect to time. So of course, there's a lot of regulatory aspects that are tied to these measurements. And similar to CO2, now we know that this technology has been deployed for monitoring water floods, to monitor steam injections, to monitor before and after effects of fracking. So again, we have the sensitivity basically to record all of these types of physical processes within the reservoir. But really going beyond the seismic, and I think what I want to showcase here is what else can we do besides the seismic, or this traditional exploration seismic. And perhaps to go back a little bit into the instrument, and the only slide I will have on that is the following. And basically, now after many years of deploying these instruments and many engineers and scientists using this technology, now we've come to understand that the response of these tools is actually very broadband. So in this specific case, what we call this DC coupled DAS unit, essentially now we understand that we actually can sample not just bandwidths at the seismic level. So traditionally seismic, let's say from 5 to maybe 100 hertz, that's where we traditionally have lived. But we do know that now these interrogator units actually are very sensitive at significantly lower frequencies and to actually very, very long periods. And at those very long periods, again, we start to measure other physics. So this is, we're going beyond the seismic, we're getting into really temperature, we're going into the deformation or strain. And so again, something that is very nice about these tools is that all of a sudden with the same instrument, you can do different physics. And something very important about this is that these tools, again, they tend to be basically a flat spectrum. So we actually can get a lot of very useful signal without an instrument response at very low frequencies, but also at very high frequencies. Let's say if you're trying to get into sonic and ultrasonic type of measurements. But certainly on the low frequency end, again, and I'll talk a little bit about this in the following slides. But now we know that, again, as part of that strain, strain that we're measuring is also going to be thermal. So again, these tools, now we understand that they're also very sensitive to temperature. Here I have basically one DAS channel plotted on top of a temperature gauge. And here you can see the scale here, it's 10 to the -4. So here we're looking at 1,000th of a degree resolution that we can have in temperature with the same IU. So again, the nice thing about this is that basically on processing, we can basically start to separate these different signals. But also going back to the low frequency aspect of this is something that is very important again nowadays for seismic purposes. it's very common now to do FWI inversion. So here I only have this example from essentially a project. It's also a carbon storage facility over in Kami in Canada, where essentially we have used these systems to not just do the high resolution VSP imaging from borehole data, but now increasingly we have realized that our data is so rich in the low frequency end that we can take fibers. In this case, it's a fiber that we have on a surface layout. And basically this has been inverted by FWI. So again, this is taking advantage of the richness in the low frequency domain that this tool can provide. And here Q et al, they have showcased that essentially we can do this type of imaging with this type of tools. In this case, it's a shallow water, it's a shallow aquifer where essentially we're going to be doing the CO2 injection. So again, this taking advantage of that low frequency end of the spectra. Traditionally, again, we were focusing a lot on the exploration seismic, let's say more 10 to the 100 hertz, but now really by having a couple of hertz, again, we're starting to do these inversions. And certainly this has really taken over by the seismology. So certainly for passive monitoring for earthquake seismology, nowadays there's a lot of applications, certainly a lot of academic groups who have really adopted this technology, which again is something very exciting, because all of a sudden we start to see a lot of measurements that previously were unheard of in the seismology world. So in this example, what I have, it's essentially an array of fibers, essentially a 10 kilometers of fiber connected to one of our older legacy interrogator units. And this fiber is actually located close to the San Andreas. So this is data from Southern California. And of course, this is a very heavily instrumented place in terms of broadband and shortband seismometers. So what the team at Caltech has been doing, and they've been using these interrogators already for a few years, is essentially check the seismicity and see what can you detect with these tools instead of our traditional broadband network. So when you look at the fiber, again, of course, this gives you very high receiver density. It gives you a lot of data, large volumes of data from which you can really look at a lot of the scattering and source processes. But something that was very interesting here in this specific study was that, again, you have a Rolls-Royce seismic network, and then you compare it against a DAS. And for a long time, we used to question, well, how sensitive these DAS systems are. So the Caltech people essentially tried to answer that question by analyzing all of the seismicity over a period of a large aftershock sequence a couple of years ago. And what they essentially showed was that essentially the DAS system and the traditional seismic network were actually recording most of the same events, but they did realize that essentially this high density array in the DAS was actually enabling them to actually detect a significantly lower magnitude. So actually they were able to show that you could lower the detection threshold almost a full order of magnitude. And of course, this also carried a higher event count. So again, we have now a richer earthquake catalog seen by the fiber compared to the conventional network. And this is important not just for seismology reasons. Increasingly, again, when we're monitoring, let's say, for example, carbon storage facilities or geothermal fields, there's a regulatory aspect that essentially is telling operators, well, if you generate events after a certain magnitude, then that's a problem, and we need to be able to flag them. So here I just put an arrow here, the area where I have essentially the magnitude threshold. In this case, for the US, certain regulatory frameworks, the protocol is 2.7 magnitude, where you need to essentially report it. But you can see that essentially most of the events that we are locating and detecting with these fiber optic arrays are way below that. So now we know this gives us the peace of mind that the sensitivity of the system, and mind you, this is a legacy system, is providing that sensitivity to detect this type of information, this type of data. Of course, this is still on the very low frequency. So again, we're looking here for some of the larger magnitude earthquakes. Again, we're looking into a couple of hertz. Certainly from a lot of these developments, before we got into seismology, of course, we did a lot of work in unconventional reservoirs. So there we spent a lot of time looking at microseismic. So essentially there we were looking at essentially at places where you would have wells where you would be injecting something into the subsurface and basically generating these fracture networks. And for a long time, again, we have been using conventional geophone networks to record microseismic data. Now we know that we can also use fiber optics to essentially instrument these injector wells, instrument monitor wells, and have a full three-dimensional network of DAS receivers within the reservoir. So again, this has been done for many years. Again, we have all of that microseismic data, but just to change gears a little bit on beyond the microseismic, something that has been very instrumental right now in development of unconventional reservoirs, and now we're starting also with geothermal reservoirs, is essentially what happens with the strain. So again, when we look at the very low frequency response on the DAS data, there's additional information besides the seismic events. So traditionally, when we take all of those waveforms from the microseismic, we're going to convert those into dots, these clouds of dots distributed in 3 dimensions, basically just doing our 3D mapping. And what we have seen in this case, it's from a vertical monitor well. Here, these dots, hopefully you can see them in your screen, but all of these dots are those microseismic events. Here we're just plotting them in depth with respect to time. And again, we have done a lot of work on this microseismic. There's a whole industry around microseismic and unconventional reservoirs. But what fibers brings to the table is the strain measurements. Again, by focusing now not on the seismic realm, but in the very low frequency end where we have the strain, basically the stretch and compression of those fibers, we can look at the strain fronts. So in this example, again, as we are generating this fracture network, what we realized was that, again, the microseismic was only providing a certain picture of the subsurface, and actually it was very limited. Basically, we were only generating microseismic events at very localized depths in the reservoir. Now, the fiber, given its sensitivity at the lower frequency end, we could actually track that strain front that actually indicated us that essentially that fracture network was propagating upwards, but a significantly a large amount compared to what the seismic was doing. So here the opportunity was, and the opportunity is, that essentially the fiber optic enables us not only to look at the seismic, but also to the aseismic response, basically looking at this strain front. And again, there's a whole industry now of diagnostics that look only at strain to monitor these fracture networks. So again, all of this technology, and the exciting thing about it is that really once you have that piece of glass on the ground, the interrogator, basically you're measuring all of these with really the same system. So going perhaps a little bit changing gears again, besides let's say the traditional kind of like energy and exploration side of things, just touching a little bit on the earthquake side, because I want to get into other applications of fiber. So again, this is one example. This is a fiber. It's a long fiber. So this is a 100-kilometer earthquake record. For those of you, you can see here a clear P and a clear S wave. This is from a magnitude 2.4 event. Again, located 100 kilometers away from this fiber. So again, telling you that the sensitivity is there for regulatory purposes. And again, this is a fiber. Actually, this is located in the eastern Sierra Nevada in California. So this is outside the Long Valley caldera, for those of you who are maybe familiar with earthquakes and volcanoes in this area, in this part of the world. But basically, again, we have been recording again data in this specific area, very, very active seismically. But here the interesting part is I won't deal anymore with the earthquake. I think for most of us, we are probably very familiar with it. I'm going to focus a little bit more on the noise. So here what's exciting again in this case is that this is a fiber that is actually deployed along a freeway, and it goes a little bit off road. I'll show you in a little bit. But here the important thing is that the same fiber, again, we can also detect other types of noise. So I'll go back a little bit on the fundamentals of the system. So again, we have been using them to detect seismic for a long time. But at the end of the day, again, when we are sending these light pulses down these fibers, the actual measurement that we're getting out of this is actually a strain meter. So you can think of this as a strain meter. Here I have an example from Peter Howard over at Berkeley, who has been doing very exciting work with these DAS systems. And this is basically here I want to explain a little bit this what is the strain story from a more infrastructure point of view. So this again, it's a road essentially that was paved, and actually there was a fiber deployed along this road. So then what Peter and team essentially ended up doing was recording different types of data with different interrogator units. So here what they show here was that essentially, let's say if you have a car, again, since this is a strain meter, of course, there's going to be a portion along the tires where, again, those channels essentially are going to be sensing basically a push, and basically outside of the tires, you're essentially having a little bit of a tension. So this strain measurement on a road basically will look something like that. You could say, well, that looks almost like a refracted arrival, but it's actually a truck that is being driven along that road. So here you have again time, and you have the distance where you have the fiber. So again, these things are very sensitive to track these types of vehicles, these types of movement. And again, this also has added a lot of applications for sensing other things. Again, really using something that was initially designed for seismic. Now we're starting to use it to monitor roads. And something exciting about these interrogator units is that, again, you can change basically the spatial resolution to focus. Let's say I'm going to focus on long wavelength earthquakes, or in very short wavelength, let's say trucks or a bicycle, as I will show in a couple of slides. But again, as more and more people use these type of tools, now we are in a position basically to just on processing, just on analysis, and by understanding how these interrogators work, we can basically track different processes. So this is the waterfall display, again, that same fiber, that 100-kilometer fiber over in the Long Valley caldera. Here I kept here I was going to call it a microseismic. This is actually a larger earthquake that we're recording, but here the focus really is all of these strong noise, which is actually the vehicle. So in this case, the fiber, again, this portion of the freeway, of course, it's there's a lot of traffic, so you do have a lot of events. Then the fiber goes off-road, so we don't have as many vehicles in that portion of the fiber, so things get quiet. So this is important because increasingly there's been also quite a bit of work on now using fibers that traditionally have been used for telecommunications, a lot of dark fiber that is available out there that now is being used to monitor infrastructure. So we have a group in OptaSense that focuses on this, but basically by tracking, again, with respect to time, again, this here I have the vertical axis is the distance along the fiber, along the road, and then horizontal axis is the time. So again, here we're recording data over a few days. So you see a lot of trucks. For those of you in the exploration geophysics side of things, this could also even look almost like a blended seismic record where you have, again, all types of events overlapping. But again, we use this data, and increasingly the analysis that is done, and mind you, the analysis most of the times uses tools that we have been using in geophysics for a long time. So metrics like average speed, how long it takes to take from one place to another, if there's traffic, things like that. And these are things that actually are becoming basically the norm nowadays. Actually, we're starting to monitor cities, monitor roads using this technology. Just as an example, here I have a fiber that is located over in Pasadena. So again, this is using that long range system where essentially before, incidentally, we did happen to be acquiring data before and after the pandemic. So essentially what we're using is essentially taking all of these data from a data set very similar to this, where again, you can have these events from vehicles moving at certain speeds. So when we can parameterize all of that speed data, essentially this team, this is a paper that was published in Nature a couple of months ago. What essentially they were able to track was that by looking at the DAS data before and after the pandemic, actually they were able to show that the traffic volume before and after change, of course, changed a lot. Of course, we went into lockdown, so we stopped using our cars for a long time. So all of a sudden, before lockdown, again, you have very large traffic volume. After or during the pandemic, again, you start to have a significant decrease on it. But other attributes, and again, as more and more cities start to adopt this type of surveillance, you can also track different things, let's say for traffic control, how to optimize our stoplights. So for example, in this distribution that I have here on the right side, essentially what I'm showing here is, again, how the velocity along a stretch of the fiber change, or the speed of cars across a stretch of the fiber change before and after the pandemic. So prior to the pandemic, this part of Pasadena, it's really hellish traffic. So again, you move at a very low speed. During the pandemic, actually, whichever number of cars was driving, actually, they were driving at the right speed. So again, all of this type of data is available. Again, these are not fibers deployed for this, but they just happen to be there. So we can just connect to them and use them as sensors. And in the same way that we use these fibers, let's say, on roads, there's also other fiber available. Again, for many years, we have been monitoring, for example, pipelines. So this is an example from a pipeline over in Mexico. So here I have almost 300 kilometers of pipeline that we are monitoring with DAS. And certainly here, what I show here just as an example, it's an earthquake. So this is a large earthquake over in the Pacific coast of Mexico, where essentially that pipeline data essentially recorded this earthquake. So again, here I'm just plotting it as a waterfall display. Again, I won't get into the analysis of the actual waveforms, because actually, of course, this fiber was not deployed to record earthquakes, but it was actually deployed to actually monitor the actual pipeline, to monitor the integrity of that pipeline, which is, again, one area where fiber optics has been used and really has gained a lot of traction over the last I would say 10 years as one of those key technologies to monitor how these things operate and the integrity of these things. Because let's say in a pipeline, again, we're not going to be monitoring earthquakes, but there what we're going to be after is, let's say, if someone comes in and starts to dig or starts to damage a pipeline, there's going to be some sort of response. And again, it will look a little bit almost like a seismic wave. So again, a lot of the tools that we have used in traditional geophysics, again, are being used to also detect other types of events. In this case, just happens to be basically this what we call a negative pressure pulse for when you perforate one of these pipelines. But also, let's say you have a specific leak coming from these pipelines. Again, it's something that we can use this technology basically to detect that orifice noise and really track where the points of intrusion are. So oftentimes, certainly this certain areas, pipelines are a critical asset. So we want to make sure that the safety and integrity, you don't want explosions and things like that. So fiber is being used to deploy this. And again, the advantage of distributed sensing, again, is that it gives you that high resolution sampling to basically pinpoint exactly where the intrusions are. So now we have basically a whole set of products that essentially will detect these events. They'll tell you, oh, I have my specific intrusion or whatever event at a certain place at a certain time. So you don't need to populate everything with cameras. Basically, you can have an invisible sensor just telling you where things are happening. And similar in this case, of course, a leak detection is a very clear type of intrusion. But other aspects, again, it can be perhaps what we want to monitor is people approaching this fiber even before they start to dig. into these pipelines, we want to essentially track as people are approaching. So going back to that analysis from Peter at Berkeley, as part of his test along that road where he connected that ODH4 system, he also tried it with a bicycle, and he also tried it with a person. So here essentially you can see what happens as you start when you are running. Essentially you're going to be off the ground for a little bit, so that's why you have kind of like these discrete type of events as you move in time and along the depth, along the distance of the fiber. So by detecting these types of signals, and again we have now all of the analytics to basically say, oh, well, it's a person walking versus a bicycle driving or riding along that fiber. So we have again all of these tools basically to identify whether it's a person crossing a border or approaching a perimeter. So again, fiber optics, it's widely used nowadays to do perimeter security. So again, not just to track vehicles, but to track as they approach certain portions on the fiber, but identify areas where you have more activity. Could be people crossing a border in a specific location. So again, a number of applications. Again, we have a lot of tools to basically detect and classify different types of activity. And traditionally now these types of tools will integrate to other security systems. And certainly something very important, and I think something that really has changed from a permanent monitoring point of view is that it is actually a permanent. Traditionally with seismic, we have focused on perhaps on snapshots of what's happening in a place. We acquire some active seismic data at different times and then look at the differences. Now fiber is actually enabling us to very low cost really acquire data continuously. So this really turns it into a very versatile type of sensor. I'll talk a little bit about different applications. So this is for in mining. So it's a fiber that essentially deployed around the mine. So in this case, it happened to be that there was a small collapse. So there was a rock fall that again was very clearly observed by the fiber. So again, we can pinpoint exactly at what time and at what location along the fiber the incident happened. So again, of course, this has implications for management of different infrastructure. Certainly mining, that's a very important aspect of things to track this type of collapses. But again, these are systems that are permanently recording data. In this case, of course, it's a large signal. Basically, it's a collapse of from a rock fall that it was detected by the fiber. But beyond that, again, there's other types of analysis. Again, in this case, you can think of this as a signal that is going to radiate very broad range of frequencies. But let's say if we go back a little bit to our traditional geophysics, our traditional seismic analysis, again, we can use these permanent sensors and basically not only use active data, but also use passive data to essentially do images of the subsurface. So again, going along the same theme of mining, something that we have been doing for slope instability. Now, increasingly, we're seeing assets where essentially we have fibers that are deployed along hills. So something that we have done with this type of data is essentially track track passive noise. So again, we're permanently recording data. So we can use basically interferometric seismic gathers of the subsurface, again, in different portions of the fiber. So for those of you who do surface wave analysis, basically here what we're doing is taking, again, all of that interferometric data, all of those virtual source gathers to essentially have a measurement of, again, virtual sources that we can use to illuminate the subsurface. So part of that analysis can be used with this frequency and velocity dispersions that, again, are a measurement essentially of the velocity in the subsurface. So again, there's a lot of applications that are used for this, but really for slope instability, essentially here what we're after is identifying areas where you have anomalous velocities that could be identified or interpreted as potential risk zones. So areas where, again, if you may have a tailings dam that could fail, or if you have a slope that all of a sudden could start to fail, again, this would allow you to use passive seismic data to do that type of illumination. And it's exactly what we did in this specific location, where essentially we have this slope. This is in the UK, so it's quite a rainy place. So we do see that there's areas where essentially we have very, very slow velocities that are being mapped by these surface fibers, and that are indicative, again, of areas of potential problems. Of course, seismic, as I mentioned, provides you a snapshot of where things are happening. Basically, you need to do this more frequently to keep track of things. But at the end of the day, by having the fiber as a permanent sensor, not only can we have a snapshot of the, let's say, get an image of the subsurface, but we actually can track what happens as the weather develops. So again, here this using the same fiber, but here now I'm using this waterfall display. Here, vertical axis is time, horizontal axis is the distance along that loop of fiber. And again, going back to the strain measurement, of course, the strain measurement is basically telling you, well, how much that fiber is deforming. Where are you stretching it? Where are you compressing it? So in this case, it happened that part of that fiber was actually deployed on, let's say, more farmland. I'm going to call it a little bit more consolidated type of ground. And here I'm showing the other portion of the fiber, which is really on the slope. And again, here we have been tracking this actually for already a couple of years. So here I'm just showing an example of what happens right after rainfall. We start to generate a lot of strain. So all of a sudden you start to saturate the rock. You change the strain conditions to the point that you start to have a little bit of a slide on this specific location. So if we were to take just a couple of channels from this data and display them here in this 2D plot, again, here you can start to see as you start to increase rainfall, basically you start to build up, again, strain that all of a sudden you start to have an induced ground movement in the area. So again, certainly this has implications for infrastructure monitoring. Of course, tailings dams is one of those aspects, but there's other places where you have, again, cities or towns located very close to slopes. So again, this type of surveillance has a very, very big social implications. And again, in this case, the strain, of course, is interpreted purely as that mechanical deformation. But something that I mentioned very early on in this talk was that, again, these tools not only are sensitive to this mechanical strain, but you're also going to have a component of temperature. Again, now we understand that the very low frequency end of things, we can essentially track minute changes in temperature. So what we have done, and again, this is something that came out a lot of work on monitoring wells. Now we understand that essentially a lot of the signals that came not from the geophysics side, but let's say from the petroleum engineering and the production monitoring side of things, a lot of the signals that we're measuring are actually thermal signals. So in this case, what I'm showing is essentially a well that essentially is just being turned on. So again, we don't have any signals prior to production. All of a sudden, you start the well and you start to look at the very low frequency, what we call the Rayleigh DTS. And here again, as I mentioned, we're looking at very, very small temperature changes. So here we're looking at thousands of a degree that we're measuring essentially as the fluids start to propagate through that environment. Again, we can essentially look at a data that looks like this. And if I don't tell you that this is a production monitoring, people would say, oh, that looks just like a shot gather, kind of like a river seen upside down. But indeed what's happening is that actually we're measuring essentially these velocities that we're measuring here. It's actually fluid velocities as they start to propagate in the subsurface. So what we can do, again, by looking at this very high sensitivity thermal data, even though you're using a DAS box, is that, again, you can calculate these flow velocities. And traditionally, production engineers will use this type of flow velocity information to get essentially make an assessment of, well, where the fluids are migrating, how fast are they migrating, where are you producing, where are you not producing. So again, this type of petroleum engineering application, again, is something that came from fiber. And I can tell you that these algorithms, this specifically, is something that was developed internally by Conoco, by Gajin, who is now in Colorado School of Mines. But this is actually using all geophysical analysis. So there's really not much petroleum engineering going on here. It's all velocity analysis. Here's a semblance gather using just different types of signals that the fiber optic is providing. And this besides a wellbore, there's other applications for temperatures, as I'll talk in a couple of slides. But here I just want to introduce a little bit how these same fibers will track some of these fluid movements as they enter a wellbore, will capture their velocities. So again, we now know that the tools have the sensitivity to track those types of signals. And I'll change gears completely and I'll get back to temperature. So don't get me wrong, I'll get back to temperature, but I'll take a detour through Japan. So this is a fiber that is deployed offshore Japan. So it's offshore Muroto, southern Japan. So it's a long fiber. So it's actually a 200-kilometer long stretch of fiber. So we were using here our one of these long-range systems, our 5th generation system, to monitor seismic. So again, we recorded data over a period of weeks. This was actually part of an ocean bottom cable survey. And initially, again, I won't get too much into the details of the seismic side of things, but it was essentially an active seismic source. So again, a lot of data was recorded here. Just for sense of scale, here I'm looking at 50 kilometers worth of data, and these are actually we have 50,000 channels. So it's actually, these are very large data sets. And of course, you see your traditional direct arrivals. You have some reflected energy. Again, I won't get into the details of the imaging side of things, but I will mention that essentially, unfortunately here I can see that I'm overlapping the display, so you cannot see the full spectra, but suffice to say that, again, this is very rich in the low frequency end. Here, basically at the sub-hertz level. It's also very rich in all the way to the very high frequency end. So basically a lot of the high frequency data, let's say above 120 hertz, has been used for near surface characterizations to look at, again, velocity variations, very shallow, close to the fiber. Traditional reflections, again, those more used for imaging. And again, that's let's say more traditional geophysical application. Again, going back to the low frequency end of things, in this specific fiber, something that you see here, again, is you have a lot of data coming from that looks very, very, very different. So again, this is tends to be very low frequency data. It happens to be that it's actually very long wavelengths, very low speeds, very low frequencies that essentially are associated to sea waves and essentially on currents. And this actually, on the fiber itself, now after more analysis of this data, there was a paper that was just published a couple of months ago by Ide et al., where essentially they look at all of those noise responses. And again, they forgot about the seismic, they focused on this type of responses. And what they found was that along that axis of the fiber here, they're looking at a stretch of around here 10,000 channels. In this case, the spacing is 10 meters, so you're looking at 100 kilometers here. But essentially, when they started to look at this low frequency DAS data in the context of the bathymetry, what they realized was that these signals could not be explained by a mechanical strain. And what was happening was that it's actually the fiber, what was tracking was all of these eddies that were actually associated to thermal processes, associated to water mixing processes. This is well below subseismic bandwidths. So this has implications, certainly not just for seismic exploration, but let's say, when you're starting to do analysis of things like tsunamis. Of course, this is also offshore Japan. This becomes important because, again, it tells you what are the flow conditions in the ocean column. So, again, very different type of application. Again, this is a thermal analysis of currents being conducted by a team of seismologists. So, again, just as an example that, again, these types of tools are really opening the door for us geophysicists to look beyond seismic and look into other processes, and I think that's very exciting. Certainly, as the industry changes, as we start to monitor, let's say, geothermal fields, carbon storage facilities, even wind farms. Again, I didn't mention it in this presentation, but again, a lot of those assets have fiber optics. So again, we use different fiber optic diagnostics to basically track how things are operating. So again, just an example of the different types of physics that you can get out of the same measurements. And really, just to take it, just one more slide, just to really to take it out of space. So this is actually an example of actually a fiber. So this is close to one of our labs in the UK, where essentially there was a meteor that was observed. Here you see a picture here from the field, but we actually happened to have a fiber that was recording DAS data in this specific, very close to this area in the UK. So by looking at the DAS data, we actually could track essentially the arrival times. Again, you have in this case, the fiber is actually kind of like looped around the building. So that's why you have the changes in velocity. But again, using this type of data, again, by detecting frequencies, in this case, I'm looking at very, very high frequencies, we can start to, again, track other types of processes. So this is really looking more at a different domain. Again, in this case, by using the fiber around the building and other stations in other portions of the UK, again, they were able to triangulate where the entry point for that meteor was. So again, all of this is, at the end of the day, it's the velocity. You can think of this as velocity analysis, back propagation, or reverse. You may call this reverse time migration type of analysis to detect different types of features. So with that, I'll conclude. Again, hopefully I'll give you a tour of very different applications of this type of technology. Certainly nowadays, I think these new interrogator units, whether we focus in short distances, and by short we usually think of short as fibers that are less than 10 kilometers. And again, we can make these very high sensitivity with these very high resolution measurements. We do have the tools now to connect to longer fibers. So again, right now, we're starting to see more and more data sets that are getting more than 100 kilometers of fiber, whether it is, let's say, in the oil and gas industry, subsea wells, but increasingly seismology, increasingly offshore surveillance, where again, we are connecting to telecommunication fibers that are available. Again, we can use those as sensors. I think that's what, at the end of the day, a distributed sensing brings to the table, is turning those fibers that may be deployed there for other purposes as sensors that are sensitive to temperature, strain, seismic, acoustic, supersonic. And so again, very different types of physics that you can do with these types of signals. So hopefully I gave you a high overview of different applications. So certainly from energy, permanent monitoring. Again, I probably didn't spend as much time on the exploration geophysics, but again, this is what got the technology started. And now again, we're just using it for other types of infrastructure monitoring, roads, pipelines, a lot of work being done on border security, increasingly oceans. Again, we do know that there's a lot of fiber being deployed on the ocean floor to transmit data. And again, those cables usually have hundreds of fibers. So it's very easy basically to connect to those fibers and do not just engineering measurements, but also geoscience measurements with these types of tools. So with that, I open to questions, and There's again, all of the material that I showed has been published. You can go to our website or just send me an email if you want to get into any more details. So thanks for your attention again, and I'll open up to questions, Anabella.
Thank you so much, Andres. We have the first question from Juan Porras. He says, hi, how do you estimate the magnitude of earthquakes with DAS? As far as I understand, the instrument response is not yet known.
Yeah, that's actually a very good question. And the instrument response actually it is fairly well understood now. We do know that essentially right now it does depend on the interrogator. So again, there's different types of interrogator units out there. Ours, the one that we provide, it's a pure strain measurement, and that essentially can be parameterized. You can parameterize a moment magnitude as a function of that essentially displacement. So essentially turn the strain into a displacement and turn that into a moment magnitude. What we have realized is that actually the fiber data is so rich in the very, very low frequency end, where you also have thermal responses, that a traditional, let's say like a Brun spectra type of magnitude tends to be not as stable. And one of the approaches that have been followed, and again, it's not set in stone, but one of the areas that, one of the applications that we have used is essentially use what we call maximum strain to estimate a magnitude. So that seems to be a proxy for magnitudes that are actually can track overall performance and overall sensitivity for seismology purposes. So again, depending on the instrument, depending on the DAS, there's strain rate instruments that will have a different type of slope in the low frequency end. But again, depending on the tool that you use, again, there's nowadays we have the knowledge to basically make a fairly reasonable magnitude assessment.
Thank you. Chris Willesee asks, could you comment on the development of multi-component recording for microseismicity using DAS?
Very important question, and yes, so far I certainly didn't go into that. All of the measurements, of course, this is a single fiber, single axis measurement. So we do measure basically a projection of the entire wave field along the axis of the fiber, but as you mentioned, this is not a three-component technology. There has been some theoretical developments, and again, this is something that was done early on by Ivan Lim over at School of Mines a couple of years ago. And there's been a little bit of follow-up work on that, but there's configurations of fibers that when put into certain types of cables, you can have a response that is closer to a multi-component type of size. Those cables are still on the costlier side of things, so they haven't been commercially deployed, but the theoretical framework has been developed. Right now, when it comes to earthquake monitoring, what we have done is really taking advantage of fibers in different geometries, whether it is borehole or surface, and a combination of them to basically do a three-dimensional analysis. But yeah, that's one of those areas where again there's a lot of work that has been done on the cable construction to enhance different types of modes in these fibers.
All right, next question. Is coupling an issue for events with frequency below 1 Hertz and above temperature effects?
No, so traditionally, that's an excellent question. When we started to go into wells, there was always a question, well, are you going to having the fiber behind casing or inside the well, or just hanging loose inside a fluid environment? Now what we have realized is that actually, particularly once you go to those very low frequencies, you're looking at essentially actually kind of like longer type of wavelength. What we have realized is by the nature of the measurement where we have this gauge length, this spatial resolution, and we're interrogating essentially a portion of the fiber. And what we have seen is that particularly once you go into those low frequency regimes, the signals actually become very, very stable. You don't have as many high frequency fluctuations. So the data tends to be fairly stable whether you are in a coupled environment or a non-coupled environment. So it does come, basically what happens is that the noise arrivals that you will have from poor coupling versus another, the signals are still going to be there, but essentially what will be different is the noise present in the data. So again, coupling, again, I think we have realized that it's not too big of an issue. Let's say in areas where the systems are not as well coupled, let's say you may have a little bit of ringing in some places. The other thing that we have found out is that we have such rich data sets as far as the receiver density. Again, these things, you can think of this almost getting channels every meter if you want to. And that gives us a lot of receiver density that also allows us to do a lot of array processing. So I think right now in the processing, I didn't get into it in this presentation as much, but that's a whole field where essentially we have shown that this array, these dense arrays are really enabling us to subtract different types of noise features that we may see on the data. So at the end of the day, we do have the signals of interest. And again, it does come down to oftentimes to what you may do on processing.
All right. Hisato Konishi asks, could you tell me about some disadvantages of measuring only axial strain, horizontal component by DAS?
Well, disadvantage, I probably will need a follow-up question on this one as to which specific application. I can say as far as, let's say, from a traditional seismic exploration point of view, by measuring, let's say, that horizontal component, there was a project, this is something published by Andrei Bakulin and team from Aramco a couple of years ago, where essentially they use surface fibers now on the surface, and they process that fiber as horizontal components. So, of course, in that case, basically the access of the data was not optimal for a traditional, let's say, traditional seismic reflection survey, because again, the angles of incidence were off from the fiber. But that was from a seismic point of view, from an exploration seismic point of view. For example, what we do in a strain measurement, let's say in unconventional or in geothermal reservoirs, as you start to generate those fractures, and again at a very low frequency, and even though those signals are arriving perpendicular, essentially perpendicular to the fiber along that horizontal axis of it, essentially we still have, again, at that very low frequency, we have actually a very rich data set. So we can see very clear arrivals of essentially of the opening of the fracture. So perhaps another way to answer this question is that for certain measurements, perhaps the orientation of the fiber is an issue. But let's say for other measurements, let's say for strain measurements, actually it becomes an opportunity, because again, it allows us to see as the fracture reaches the fiber optic, it will let you see the opening of the fracture right at the tip, and it will allow you to see the stress shadow in the surrounding channels. So again, that's a very valuable data set that is being used increasingly for geomechanics analysis.
All right. Doug Christ would like to know how much these systems cost.
Oh, that's a $1 million question. So these are there's a range. So again, depending on the features that you're looking at, let's say some of the earlier generations of DAS data, you're probably looking somewhere around, I don't know, $50,000 for the IUs. The more Rolls-Royce ones, you're probably getting into the $250,000 type of range, depending on the features that you have. This is just for the interrogator units. Again, nowadays I can say that there is a lot of options now on the market, again, with different types of features. So definitely important to look when you're purchasing these things, see what types of features you want. Some of them are better at high frequency, some of them are better at lower frequency, some of them get you longer fibers, some of them get you shorter fibers. So again, there's a whole range of flavors of these, but I would say from 50,000 upwards, probably kind of like the standard, depending on the features that you are after.
Thank you. Mohammed Musa, what about high resolution multi-component DAS for fracture imaging?
Yes, so high resolution fracture imaging again is one of those very important aspects that are have really changed certainly unconventional reservoir developments. So again, that's essentially when we're looking at those fracture networks in those types of settings, we have run these systems with spatial resolutions as low as 2-meter gauge length. So again, very, very short spatial resolution, and actually we can identify fractures basically at that level. So for a long time we were running microseismic data in different places, and essentially we were interpreting again things that were happening at very short spatial resolutions with a very long wavelength measurement. Now with the strain data, now we know that we actually, if the engineers are injecting every fluid and propellant every 2 meters or every 3 meters, we actually have the data to delineate all of those different fractures. So again, that resolution is there with these newer systems. And there's other interrogators out there. Again, here I focus a lot on traditional time domain reflectometers, but frequency domain reflectometer, there you can get into resolutions in the millimeter or centimeter. So there is, again, depending on the application, there is different types of resolutions that can be achieved.
I believe Mohammed has a follow-up question. Mohammed, you can unmute yourself and ask.
Hello.
We can hear you.
I thank you, Professor Andres, for this presentation. It's really interesting. I'm asking about the application of DAS for least square, reverse time migration, and FWI. I'm looking for interesting topics to write a proposal for my PhD.
Perfect. Very, very good question. And I can tell you that, and again, this is new. I would say that a lot of the uses for let's say for our seismic data, for our traditional reflection imaging, has been focused on let's say the traditional reflection, let's say from 5 to 100 hertz. I think the first paper we saw on least squares migration is probably 2 years old, from the Quest facility in Canada, where again they looked at the low frequency data. They actually found out that the data is so rich in the low frequency end that they could do a least squares migration that was very rich in its content. So again, it was a stable inversion. Again, that paper was published, I want to say, 2 SEGs ago. And from the FWI, again, the FWI, traditionally, this hasn't been one of those areas of application in DAS. But now we're starting to see some people actually running data and actually running very stable inversions. And what they found is that actually you do have such a rich data set that, again, it allows you to avoid the problem of cycle skipping. Again, traditional sensors are going to have the problem, again, of that truncation in the spectrum in the very low end. We don't have that problem, which again turns this fiber data into a large opportunity to make those types of measurements. So I think right now, as more people are using this data, more and more applications of least squares and FWI will continue to come up. But again, they're really taking advantage that not only you have a rich data set, but it's actually, when I mentioned that the system is a DC coupled system, it actually means that you pretty much have a flat spectral response down to very low frequencies, which again allows you to do this type of processing.
Thank you. Okay, Yuri Starovoy. Andres, thank you for the interesting presentation. Regarding meteor detection, was it a recording of acoustic waves that hit the ground where your DAS was installed?
Yes, that's correct. So this essentially, it's that what happens is there's going to be a pressure front as these things propagate through the atmosphere. So again, we'll generate this pulse. Traditional seismometers would have picked this up. I think they call it an N wave or something like that. But it is essentially an acoustic response coupled as it couples down into the media where the fiber is deployed. I can say that there is a lot of the applications that this fiber for this type of analysis is not really meant for meteors. I can say that there's a lot of defense applications for these types of systems that again look at that type of more supersonic type of radiation. When we're sending the light pulses down these fibers, we can interrogate at very ping rates. So depending on the system, you can reach 50 kilohertz or 100 kilohertz sampling. So again, you really can sample very high frequency data with these units.
All right. Alexander Sugar, do you use whorl fibers in your cables? Could you tell a bit more of this aspect?
I'm sorry, I didn't understand.
Whorl fibers. Are those in your cables? WIRL.
Let me go back.
Let me see, Alexander. Alexander, can I unmute you so you can clarify?
WIRL fibers. I'm not sure. Well, what I can mention about the cables themselves, and this is actually it's a very good question. Yes, as I mentioned, there's different constructions on the cables themselves. Again, traditional fibers have been just a single fiber that has just a regular jacket on it. And again, we do know that DAS systems, again, they'll have there's a radiation pattern that we call the cosine square radiation pattern on the fiber. That again, basically tells you that some waves that arrive perpendicular to the axis of the fiber are going to have essentially less amplitude than waves that are arriving along the axis of the fiber. And there's been, perhaps that's what Alexander is mentioning, is there's fibers that we call helical. So these are fibers that essentially are wound up on a cylinder. Imagine almost like a toilet paper that you put a fiber around it. And that essentially has helped us overcome some of that radiation pattern. Those types of systems are more common, let's say, in environments like surface fibers, not as much downhole. And there's other types of cable constructions that, for example, we do have a cable that essentially has a different type of jacket that essentially allows us to enhance the radiation pattern for those waves coming perpendicular to the fiber. But again, there's different ways that you can do with the cables themselves. Again, traditionally right now, I would say due to the cost of these cables, most of the traditional fiber is just a standard cable fiber that will have this cosine square radiation pattern coupled to it. I hope that answers your question. I think that's what I understand as whorl fiber.
Thank you. Okay. Yingping Li, how to distinguish daily variations of tide and temperature?
Very good question, and that is one area. Again, there's different IUs that measure. There's IUs that are optimized for temperature. There are IUs that are optimized for, let's say, for strain and acoustics. In our case, again, this DC coupled business, when we're measuring this data, the strain that we're capturing is not just mechanical, but it's also thermal strain. So what will happen is that certainly in the processing, there's going to be an interpretation aspect. So essentially where we'll say, well, we're using this type of fiber, let's say it's a gel filled fiber optic, which again shouldn't, given the environment that we're measuring, let's say if we're in a fluid environment, we're not going to be expecting as much of mechanical strain. It's going to be more thermal. So in processing, essentially what we're going to do is essentially take advantage of some of that interpretation and say, well, I'm going to separate the temperature signals out of this. Oftentimes, again, depending certainly for oil and gas applications, you tend to have different fibers with different interrogator units. So again, you can actually combine different interrogators to get different types of responses out of the system. But if you only have one interrogator measuring the overall spectra, essentially depending on the physical processes that you're going to be studying, you essentially are going to make that assumption. And there's something on the parameterization of the interrogator that we will say, well, these are actually going to be temperature fluctuations instead of mechanical strain. So again, this will depend really on the interrogator unit that you may be using as well. Some systems, for example, all of the data that I showed here uses Rayleigh backscatter. There's also Brillouin, there's Raman backscattering. Again, they're all going to be focusing in different aspects of the light spectra, which will help you emphasize certain signals better than others.
Thank you. David Berman, he thanks you for an excellent presentation and asks, what is this interrogator distance limit on fiber length? For very long fiber installations, what considerations are needed for the interrogator or fiber construction to be able to receive returns with reasonable signal to noise?
Yeah, so that's a very good question. And actually, when we first released our 5th generation system, what we call our 5X or Quantex systems, we were essentially running, we thought we were going to be just getting light up to 50 kilometers. And that's the first studies that we conducted with them. That's what we were running them on. Of course, people start to get creative, start to connect to longer cables. And all of a sudden, we started to see signals at more than 100 kilometers. So we knew that actually we actually had that reach on the systems. What's important here is that all of those experiments, and I'm not even going to call them experiments. Now these are actually commercial projects where essentially we are connecting to existing telecom fibers. So the cheapest of the cheapest cables out there that are being used to make these measurements. Of course, there is a specialized fiber that you have what we call ultra low loss fiber that again gives you higher signal to noise, gives you a higher level of backscatter. But all of this data that I showed from long distance has been using dark fiber, again, fiber just on the cheapest side of things. So again, I think as far as limitation right now, given the cables that we have connected to, we have seen like a lot of data, a little bit of more than 100 kilometers. I know some other people have recorded a little bit more than that. So I think what we have done essentially to not have that dependency on the fiber itself has been to focus on the development of essentially of the lasers and what we do with the light processing. So essentially so the choice of fiber doesn't become an issue. So right now, these newer systems basically really can connect to any type of glass. And some people may put some sort of fiber Bragg rating to get certain enhancements on certain fibers. So there's really a lot of options now when it comes to fibers, but certainly for seismology point of view, where we're connecting to fibers that have been in the ground for many years, that's just regular glass. And again, we can see very comfortable seismic data at those distances. Perhaps let's say if you wanted to go to measurements at very long distance with very short spatial resolution, you may need to change some things on the glass or on the interrogator. But again, a lot of those limitations that we had, I'm going to say up to 3 years ago, they really have been going away very quickly. I think that, which is something very exciting about the technology itself, that the developments in the IU have been so rapid that all of a sudden we're end up measuring things that we never thought we were going to be able to measure.
Right. Emmanuel Bossi, what are the expected maximum range improvements? How far we can measure coherent signals at DAS channels that are expected in near future?
Right now I know we are connected to fibers that are 200 kilometers. So I think that is basically that data is already starting to be more available. I think going beyond the 200 kilometers, I haven't seen any data on it, but again, as I mentioned, the development of this is very rapid. So right now, just based on the things that have been published, very comfortable. And again, by very comfortable, I don't mean, oh, you see hints of signal. These are actually signals that you can look into the waveforms, look at parameters from those data, and get value out of them, not just have a pretty picture of it, but there's actually information being recorded at those distances.
Laszlo Molnar, can you give me an estimation for penetration of fiber optic in monitoring microseismic events in US?
But that's a very good question. So, of course, a lot of the microseismic monitoring that has been conducted has been with fibers that are in the subsurface, so fibers that are deployed in wells. So basically, we are using a seismic network inside the reservoir. But again, as more people, and again, remind you, this technology was deployed originally by the oil and gas industry downhole. The seismology applications are fairly recent. I think the first application was probably the Stanford array that came online maybe in 2017, around that time. But prior to that, all of that was downhole. And I think from the surface arrays, now we have shown that again, we can detect events comfortably, again, let's say to the -1, to the 0 magnitudes. And again, these are deeper events that may be many kilometers away from the fiber. So I think the sensitivity on these systems, not only certainly one aspect of the performance is getting you the length, but the other performance is definitely the sensitivity. And the more seismologists have adopted this technology and they're starting to compare it to conventional seismic networks, it really has opened our eyes for us to see how these systems are performing. So again, we are detecting quite a bit of events from fairly long distances away from their sources. Traditionally in microseismic, you would have been monitoring very close to where the source of the event was, but now again, now we have shown that we actually can detect events that are farther away.
Perfect. Chisato asks, how deep did you install the fibers for the landslide example you showed?
Very good question. Yeah, so this is so there's different, that example, I want to say it is 30 centimeters. But again, this really will depend on the place where you're going to be making your study. Oftentimes, there could be regulatory constraints that essentially allow you to dig up to a certain point. So we've seen everywhere from, I'm going to say, maybe 1 meter. The deepest ones, this one specifically was in the centimeters range. So it was around 30 centimeters. It's very common, let's say, around pipelines or around some, let's say, other type of infrastructure where they may do like 0.5 meter trenches and then put those cables. But there's really a lot of flexibility there on how you sense those and how you install those.
Okay, next question is by Chaoji Wan. In LFDAF, measurement in hydraulic fractures, sometimes that signal spans for a few hundred meters, but the fracture opening can be a few millimeters. The DAS measurement seems to be oversensitive. How was the strain signal measured by DAS validated?
That's an excellent question. I wish I could get into more details on this. I'll make a little bit of advertisement. On this last ORTEC conference, there was a session on a project called HFTS2. It was a multi-fiber optic well program that was monitoring these fracture systems. And there were tens of papers, actually there were 5 sessions just answering this question. And essentially, part of that validation came essentially from modeling. So there was a lot of not just sensing acoustics, temperature, pressure, and temperature gauges, but there was a lot of geomechanical modeling that was coupled to all of these data. And it was actually all of the data actually did represent that again, that the extent of these fractures, that again, it was from significantly larger portions of Earth than what we were expecting, it was actually real. So certainly the the vertical fracture growth was something that was fully validated by other gauge data, by other geomechanical models. So, and again, as more people are modeling and interpreting these strain fields, we're actually seeing that, yes, we have the resolution to see basically that cluster level resolution, but the extent of the fractures that we get from them are actually very realistic. So we do see some, I know some people have focused a lot on the stress shadow. And again, the stress shadow, again, the fiber does have a wide coverage on the stress shadow side of things. But when you focus on the main area of the fracture zone, it is very representative of the portions that are being stimulated by the injection. So again, I will refer, and then you can send me an email if you want. There's a lot of work that was published in that ORTEC a couple of months ago.
Right, next question. Can gravitational effects be observed using the fiber? For example, moon tides.
I'm sorry, can you repeat, Anabella?
Can gravitational effects be observed using the fiber? For example, moon tides.
You know, actually, I think there was recently an example of someone doing gravitational waves. It wasn't ours, but I did see a note of it on LinkedIn. Certainly, again, when you look at this, again, the part of the advantage, and again, as people get more creative with these measurements, all of a sudden we have places where we have fibers that have been recording data for years. So all of a sudden, when you get to these super long periods, I know that there's people who are looking into that type of data and see, well, what type of fluctuations can you get? So I think the door is open for all of those researchers who are interested in looking at different processes. I can say from an instrument response point of view that, again, we are very close to DC. So again, you can expect to have like that very low frequency deformation sample to a degree in this type of system. So I welcome, again, I'll be curious to see how we can use some of because there's a lot of data nowadays. There's starting to be more data repositories where, again, questions like this can be better answered. But I do recall someone talking about a measurement like this fairly recently.
All right. Next question by Brad Artman. Are interrogator providers open and honest about the data they record and provide? How large are these data sets? Are there standards in format yet?
I'll start from the last to the. I'll leave the first one to the end, Brad. Thanks for asking it. So large. How large are these data sets? So they're very large. Again, depending what you want to measure, they can be intensive. So again, let's say the newer system. Let's say we're recording, let's say 50,000 channels. Imagine all of a sudden, depending on the ping rates, again, we can basically send light pulses down these fibers at very high rates. So right now, for example, we have a system in the North Sea where we're injecting 10 kilohertz of data and recording, again, those 10,000 channels. And that essentially generates terabytes of data a day. So in that case, the application does look into fluid processes and into high frequency monitoring of devices. And so again, that does, you do generate terabytes. For some more traditional seismological applications, again, if you are happy downsampling things to, let's say, more seismology standard 250 hertz type of data, again, you can turn those volumes into the gigabytes. But again, part of the opportunity of these systems, again, is that you have the ability to monitor very high frequencies and very low frequencies. We do have developed a lot of infrastructure to stream a lot of the data live. And again, imagine this as Netflix of DAS, where essentially we send every byte of data to a remote processing center. So the technology is there, so you can do the processing that is needed. But yeah, these are volume intensive data sets. as far as the standards go, I would say that a lot of work, again, this being a technology that started in the oil and gas industry, many people are starting to use what we call the PROTML standard. So traditionally H5 format has been starting to be more accepted as the usual. You can put a lot of metadata into these types of files. We still see as a standard, and certainly for seismic applications, people recording is still SegWi. Still the option is out there, but I do see more and more people using H5 as the format of choice, particularly for permanent monitoring. Now, as far as the last one, are interrogator providers open and honest about the data that they record and provide? I think we are. I think certainly on the when you purchase these systems, you know essentially what type of instrument response you have, whether it is a strain or a strain rate, and the type of measurements that you can make with them. So again, right now I would say it's fairly commercial technology. So I think the standard certainly for us in OptaSense, we do provide, when you purchase this system, the specification of the shape of our spectrum, and as far as the testing goes, again, coming from the energy side of things, CFOM has developed a lot of the standards for how to calibrate the systems, how to assess the noise levels and things like that. So all of the vendors now really do have that type of report available for you guys to use when you're purchasing or using this type of data.
All right. Mohammed Musa has a couple questions. One, at slide 21, when you explain Raleigh DTS, is this research now at Colorado School of Mines? And he also asks if you can suggest references to read more about that.
Yeah, excellent. And if you send me, my email is there, you can send me an email. I can share some more references. But yeah, this is certainly something that Gejin at School of Mines has continued to do. And he has a couple of students and postdocs, Alexei Tito, who have continued to do a lot of work on this temperature sensing. I wouldn't call it too much of a research. Again, it really has become a commercial product. So there is operators that really use this data to measure temperature fluctuations inside wellbores specifically. So again, there's a lot of already a breadth of knowledge on these specific applications, and certainly now there's other people who are combining some of these low frequency thermals from DAS to conventional DTS and get other types of proxies for strain and pressure and things like that. So it's really an exciting field. Again, it's the fundamentals of it are fairly simple. You have a fiber, and then you connect your interrogator, and then just get value out of all of those measurements.
All right, and the last question, just in time. What is the estimated cost for recording a 2D line surface compared with traditional seismic single sensor recording, for instance, a 5-meter group interval?
You know, that cost, I'm actually, I can quote by email. Traditionally, the way these things are priced, it's basically on a day rate. So similar to what you would have with an array of geophones. You essentially would have a fiber. Usually the fiber itself is fairly cheap. Particularly surface fiber. You're looking at cables. The most simple cable of fiber optic may be, I don't know, maybe 30 cents a meter. Once you put it with the cable and everything, you're looking at fairly low cost acquisition. And the interrogators, usually you're looking into the day rate. So maybe on the tens of thousands of dollars for day, and that basically gives you an entire survey in one day. But again, it really depends on the surface conditions, on the type of survey. Again, most of the exploration, most of the seismic data that has been acquired for let's say for this exploration side of things has been for borehole seismic, and there you have clear cost savings when it comes to deploying geophones, because you can deploy these fibers basically in wells that are producing, so you don't have to shut them down, and it's faster to have these systems in place. So, but yeah, you can send me an email. I'll be happy to add more to that regarding comparisons. I can say there hasn't been as much comparisons of surface seismic versus fiber optic seismic. So again, that's still an area that more people are venturing into it, because now they're more comfortable with the radiation pattern specific to the fiber. Right.
All right, so those were all the questions. Thank you so much for this fantastic presentation, Andres. Everybody has liked it. They left also comments thanking you for this presentation. We will be posting these in the SCG YouTube channel, and stay tuned for the next presentation of the series, which will be the first week of January. Thank you all for attending, and thank you, Andres.
Thank you.
Thanks so much.
See you.
Bye.